Hi class. Today I'm going to go through examples and notes for section 1.4 and 1.5. We're going to be talking about exponents and roots, and we're also going to be talking about sets of numbers in this video. So here again, you can pause the video and copy down some notes. I'm going to use the notes here to go through our few examples. Okay, so here is what we call a power. We have two parts to it. We have the base and we have the exponent. The exponent tells you how many times to multiply the base together. So in this example, my base is 3 and my exponent is 4. So what that says is you're going to take the base of 3 and multiply it together 4 times. And this is what we call expanded form. You don't have to write this out every time. I'm just illustrating what this actually means. 3 times 3 times 3 times 3 is 81. So 3 to the 4th power is 81. Another really important thing that we're going to point out with this section is the negative being in parentheses versus outside of the parentheses. So when it's in the parentheses, it's saying take the value inside, -5, and multiply it by itself 2 times. So this is the same as -5 times -5. Well, now we apply our integer rules for when I multiply something with the same sign, I get a positive answer. So I get positive 25 there. Now, how is that different from this one? Well, really what this says, you guys, is another way to think about this is -1 times 5 squared. So if we think about order of operations, I have to actually do the exponent first and then the multiplication. So 5 squared is 25. So this is really -1 times 25. Well, negative times the positive is -25. So you'll see that actually my answers are different depending on which kind I'm given. So if the negative is in the parentheses, I multiply the negative with every single value. If it's not in parentheses, it's just one -1 being multiplied at the end. Do the exponent first, and then you'll tack on the negative. Fractions, it means the same thing. It means 2/3 times 2/3 times 2/3. Or you can think about it this way. Because multiplying with fractions, I multiply all the tops together, so 2 times 2 times 2, and all the bottoms together. So it's the same as thinking about that exponent on both the numerator and the denominator. Well, 2 to the 3rd power means 2 times 2 times 2, 8. 3 to the 3rd power is 3 times 3 times 3, or 27. So notice I kind of skipped the expanded form in that example. You'll be able to do that once you get better at it. Okay, this is just kind of a sneak peek. We're going to be getting into this a little bit later on, but kind of a sneak peek as to what this looks like. When I do a variable here and I have the same base, notice they're both an s. S squared means s times s. S to the 3rd means s times s times s 3 times. So total I have 1, 2, 3, 4, 5 s's. So this is the same as s to the 5th power. A shortcut here is if I have the same base, I can actually just add the exponents. 2 plus 3 is 5. So kind of a sneak peek. You guys aren't going to see that on this particular homework, but we are going to be getting into more of that later on. Okay, root and radical. So square roots are the ones that we're primarily going to be using. We can have other roots. We could have cube roots, 4th roots, 5th roots, on and on and on. Primarily, we're just going to be using square roots. And the square root is the opposite or the inverse of squaring something. So kind of phrasing it this way is helpful. What times itself equals whatever number you're trying to find the square root of. So in this case, I want to know what is the square root of 4. So here's where this question is helpful. What times itself equals 4? The answer there is 2, because 2 times itself, 2 times 2, gives me 4. Asking that question again, what number times itself gives me 81? 9, because 9 times 9 is 81. With fractions, you can think about it this way, the square root of the top over the square root of the bottom. So I'm going to kind of ask that question twice. What times itself gives me 25? That answer is 5. What times itself gives me 64? 8. So 5/8 is the square root of 25/64. Okay, now we're going to talk about sets of numbers. I really like this Venn diagram here because you can kind of see that all the numbers that we're really going to be working with in Algebra 1 are in the real number system. So the real number system incorporates all these different kinds of numbers. So kind of our smallest category is what we call the natural or the counting numbers, 1, 2, 3, and 4. Then a little bit outside of the natural numbers, but includes the natural numbers, are whole numbers. So it's actually the same thing, but it includes 0. Integers now are those whole numbers and their opposites, the negatives as well. And then we get into rational. So rational includes fractions and decimals as long as the decimals end. That's the terminating piece. Or repeating decimals are also considered rational. Irrational are things that go on forever without a pattern. So here's some examples. Pi, e, or the square root of 2. Those are all decimals that go on forever without repeating. Okay, so we're going to come up with just a couple other examples here, you guys. Here are some notes on their definitions exactly, but I like that Venn diagram as well. You'll notice that each of these have symbols. So natural is a capital N, whole is a capital W, integer, that one's a little weird, but it's a capital Z. Rational, this one, I always think of Q because of quotient. Rational is ratio or dividing or fraction, so quotient kind of helps me remember the Q. I is for irrational, that one kind of fits, so that's why integer is a different one, it can also be I. And then real is that double bar R that we use. Okay, so let's think of a couple more examples. So 1, 2, 3, 4, basically any whole number that's not 0 and not negative is something in the counting numbers. So I could 23, 57, 1,000,000. Those are all examples of natural numbers. Whole numbers, I could use those same examples, but 0 is also in this set. So any other examples you want to include? 5,280, 681, 0. I'm going to put 0 again because that one's kind of a big deal in the whole numbers. Okay, whole numbers and their opposites. So whole numbers, but this could also include negatives. So let's do like negative 700, positive 700. Okay, so any whole numbers and their opposite, 0 also fits in this one. Okay, rational. So this is fractions, decimals, as long as the decimals end, or they're repeating. So either one. So 1/3. I could also have positive or negative here. So like negative 0.25. This decimal ends, so it is rational. If it went on forever without a pattern, it's irrational. Let's see. Let's do like 0.9 repeating. That bar is the symbol for repeating. Okay, so those are all rational. Any number that can be written in the form. Okay, sorry. Irrational. Decimals that go on forever and ever without repeating. So these ones are really hard to come up with other examples other than square roots that don't work out nicely. So we call those, the ones that work out nicely, perfect squares. Ones that aren't perfect squares are always going to be irrational. Like the square root of 3. You can't think of a nice whole number that times itself gives you 3. This is going to be irrational. Lots of these ones. Square root of 5, square root of 6, square root of 7. And then one of our favorite ones, of course, is pi. That doesn't have a pattern and it goes on forever. So there's lots and lots and lots of ones we could come up with irrational. Infinitely many, in fact. And then all real is all of these. So, okay. So what we are going to do here is we're going to classify. So we're going to say what each number could be. Okay, so if it is a fraction, it is going to be rational. Okay, so this, I have a fraction, it is rational. So it is, I'm just going to spell them out. You could use the symbols here as well, but this one is rational and it's real. It's not a whole number. It's not an integer because I have that fraction piece with it. So it's just rational and real. Square root of 10, I can't simplify that. I can't come up with a nice whole number that equals 10. So this is going to be irrational. But irrational numbers all fall under the real numbers as well. Okay, 12 over 3. This one is a fraction, so it's definitely rational. But if you guys notice, I can actually simplify 12 thirds. 12 divided by 3 is 4. 4 is also an integer. It's also a whole number. It's also a natural number. And of course, all of those are real numbers. So 12 thirds is actually all of those different classifications. Okay, 2.68 repeating, that's our bar over the top. So if it's a repeating decimal, it is rational. And of course, if it's rational, it's also real. All of our different number systems are going to be real. Okay, that's it for 1.4 and 1.5, you guys. Thank you for watching.